Remember that a real number is called rational if it is possible to write it as a fraction. So 0.333 repeating forever is rational because it is possible to write it as 1 over 3. 0.98 is rational. -5 is rational. And here's a fact for you. Between any two rational numbers that you like, there will be infinitely many rational numbers. An easy way to see this is to think about that theorem from 2.7 where any finite decimal counts as a rational number, right? All the finite decimals and all the infinite repeating decimals. So, if you think about the number line with all the integers marked, and you think about 1 and 2, you could blow up 1 and 2 and write all of the tenths places in there, right? 1.1, 1.2, 1.3, and those are all rational numbers. You could blow up each of those subintervals even more, and you could write decimal numbers with 2 decimal places to the hundredths place. And you don't ever have to stop doing that. And so between any two rational numbers you like, you can always blow up that number line and write more and more rational numbers in between just by adding decimal places. Here's something that's even more surprising. Every natural number counts as a rational number, and what that means is the set of natural numbers is inside the set of rational numbers. Even though every natural is irrational, even though there are infinitely many rationals between every pair of rationals. So it seems like there's just gobs and gobs of rational numbers, right? There have to be way more rationals than naturals, but that's not true. The set of rationals and the set of naturals have the exact same cardinality. Here's the secret to the proof. We're going to make a 2-column table, and it's going to match up every natural to a rational with no leftovers and no repeats. And I'm going to start the obvious way. I got my 2 columns, and I've got all my naturals written down there. And so somehow, every rational number has to fit in here somewhere. I'm not allowed to have any leftovers, and I'm not allowed to have any repeats. And I think it's pretty obvious that if you write down just the naturals here, you're going to have like a ton of fractions left out. Like, where is 1/2 supposed to go in this table? Where is 1/3 supposed to go? And so you might think, well, okay, fine. Then start squishing in all of those fractions, 1/2, 1/3, 1/4, 1/5. But again, although we've got fractions here, it leaves out a lot of numbers. Like, any fraction that doesn't have 1 in the numerator is completely left out here. The big whole numbers are completely left out here. So this seems like a very difficult task, but what we're going to do is we're going to make a big array of natural numbers. And so the first thing we need to do here is convince ourselves that every rational number is in fact represented here. Remember, those ... dots mean that this thing goes forever. And think of any rational number you like. Will it be here somewhere on the table? So for me, for example, I'm thinking of 17 over 21. So that's positive. That means that it belongs up here and it has a numerator of 17, which means we're going to go out on this row to the 17th place. And then it has 21 as a denominator, which means we have to go up 21 places to get to 17 over 21. 17 over 21 is represented in this array. Any combination of numerator and denominator that you like, positive or negative, it will be represented here somewhere. So, fact 1, this is every rational number in the world. Next, we are going to draw a very cool spiral that goes through every single rational number. Every rational number in the world. And once we're done drawing this spiral, we are going to, sort of like Wizard of Oz, we're going to follow the spiral, writing down fractions as we go. So we're going to start with 0, because that was the beginning of our spiral. And then I'm going to follow, and I'm going to write 1 over 1, -1 over 1, and 2 over 1. Next on the spiral says 2 over 2, but I'm actually going to skip it because it's a repeat of a number that I've already written down, right? Because 2 over 2 is equal to 1 over 1. The next number I'm going to write down is 1 over 2. Next, I'll follow the spiral some more. I'll write -2 over 1, skip -2 over 2, and write -1 over 2. You keep following the spiral, 3 over 1, 3 over 2, skip 3 over 3, write 2 over 3. You go on and on and on forever. So here I have a 2-column table, all naturals on the left, all rationals on the right. And so here's a few things to remember. If you agreed earlier that every single rational was represented in this array, then the spiral hits every rational that exists, and that implies my table doesn't leave any rational numbers out. Also, we purposefully skipped repeats when making our table, which means that the table will not have any repeated fractions, and that means this table represents a 1-to-1 correspondence.